Whenever the country does something exceptional, the world sits up and takes notice. We feel a sense of pride. And ISRO, our space agency, has gotten into this habit of giving us that experience repeatedly. My reference is to Chandrayaan. The world can't stop gushing about what it has achieved, how it has achieved, and they still can't get over the fact that we can achieve something as fantastic as that at such low costs. Obviously, everybody wants to know what is it that is happening with ISRO, where are we headed, what is in store in the future expeditions or our research endeavors. And to tell us all about it, we have somebody who needs no introduction. In fact, everything that you want to know about ISRO and India's space program, he is the right person. He is the chairman of ISRO, Shri S. Somanath. Thank you so much for having us here and agreeing to speak to us. And congratulations to you on the fantastic success. So let us start with something which I want to ask, because we have gotten used to getting surprises from you. And I'm referring to the hop that Vikram did on the moon surface, which was not expected, came as a very pleasant surprise. Now tell me, on the 22nd, when the sunlight starts beaming on to the part of the moon where Pragyan and Vikram are, what do we expect?
With all our confidence on what we did for Chandrayaan 3, the Vikram lander and the rover, and also of the confidence that we have based on the test programs, we are hoping that both of them will come on. And it's important that both should come on. Coming on means that the electronics in the system should be functioning such a way that we should be in a position to send commands to it so that they will obey us when we want them to do something. And if it happens on 22nd, it's going to be history, because surviving such a very long temperature for long duration and making sure the systems work again is really going to be a tough thing, as all of us know.
Was it tested here that at such temperature, if you can withstand such temperatures for such durations?
See, what we did is we tested it in temperatures of similar nature. Of course, especially the rover, the Pragyan, has been fully tested. But when it comes to Vikram, I can't say that everything is tested. It is such a huge item which can subject to such a low temperature testing. But many of the design heritage of the systems inside the Vikram lander and Pragyan being the same, we are hoping that whatever test we did on Pragyan should be sufficient enough to give confidence to the Vikram as well. But there are still elements within Vikram that could go wrong. But everything need not work in Vikram for the relifing of this whole thing. At least if it's the communication system work and the primary computers work, we should be able to command it and then make the Pragyan rover once again.
So the command goes to now Pragyan or to Vikram?
It actually received in Vikram. Then it need to be sent to Pragyan for it to do so the communication is established between the antenna on the Pragyan to Vikram. So this communication channel should be open for either to send a command or receive a data, like the cameras. You can see the cameras, two small cameras in front. So these are the cameras. So these cameras should take pictures. And this is the one who took the picture of the Vikram on the moon, which is a very classical picture.
That's right.
So these cameras, to function and bring the image back to Earth, it has to communicate to Vikram, and then it has to communicate back to Earth. So that channel should be open.
Tell us the hops that it takes during communication. Supposing you want it to that ramp to open and Vikram to or this Pragyan to roll down. How does the command go from here, and how long does it take? What is the exact route that it takes to go there?
See, the commanding is a special activity in which there is a series of commands. It's not just one command, you now come out. No, it's not like that. There are series of commands which need to be uplinked. And what we do is we uplink all of them. Then most of the commands are timed, that you do it, execute only at this certain timing. So there is a clock running inside. There is a reference to that clock. So we send all the commands up there. then it registers inside the computer memory. Then we read back all the commands that and then check it again whether it is received and stored in the appropriate location correctly. And this verification goes. And after all this verification is done, then you leave it to execute. So it will be executed at the time which we have planned a priori. So while it is actually getting executed, we don't do a real-time commanding. You understand?
I see.
So we do the whole commands are uplinked. If you want to really do a real-time commanding, that's also possible.
How much time does it take for a real-time command to be received?
See, the signals travels at the speed of the light. So the moon and back, it takes few seconds, 1 or 2 seconds at the best.
And
not even that much, it's actually much lesser. So it can be reasonably real-time, but then real-time commanding is not a preferred option in most of these cases, except, see, if you want to get, if it is moving, it has seen a obstruction, want to do something, or some of the attitude orientation. So camera or antenna need to turn and look at the ground station a little bit. So we want to little move and then see whether it responds.
So that is the real-time commanding.
Such thing we can do in a real-time.
And if you want to orient the camera in another direction,
yeah,
and you give a command, how long does it take?
It will do in a matter of
seconds.
1 or 2
and
seconds.
You see the response
immediately. You see the response.
So when you receive pictures from the cameras on the moon or wherever, what is the speed at which you get this data?
There is a difficulty there. See, if it is an orbiter like the Chandrayaan 2 orbital where there is a high resolution camera, we have a certain transmission rate which is decided by the band in which you are using. This time we are using X band, sometimes we use S band and different bands for communication. The throughput data rate is decided by the band, the signal power, the antenna in the ground, the visibility, etc.
Correct.
So through that decides the rate at which the data can be transmitted. And it also needs to have power. For example, if you want to take a picture taken by Pragyan to be sent to rover and rover to ground, it takes actually hours for sending one picture. Reason is simple, because the power available on board of this Pragyan is very low. The battery capacity is very less. It doesn't have huge power. So minimizing power is one way to minimize the data rate. So we minimize the data rate from here to this so as to save power, so that it lives longer, because the amount of power generated is just from this panel.
Correct.
And the sun is not illuminated very bright on it. It's almost at the fag end of its life. So we keep the power very low. So typically a picture takes very long time from Pragyan to reach. But if it is a camera on the Vikram, it could be faster. But if it is from an orbiter which has a higher gain antenna, then it could be still faster.
Still faster. Okay.
So we do, say for example, in remote sensing satellites, we take images throughout, and they are sent in gigabits per second speed. So it's possible to send at very high speeds. It's all limited by the onboard power.
Interesting. What are the next things we have in mind for Aditya now? What is happening? Meaning, what exactly is happening with Aditya?
So
now?
Aditya, after its earthbound maneuvers, which was going higher and higher to almost 1.25 lakh kilometer, now it has now left Earth from the highly elliptical orbit.
Day 4 yesterday, no?
Day 4, yeah, yesterday. So it started its journey towards the Lagrangian point, L1. It will take almost 110 days for travel from here to reach there. So right now nothing more need to be done. Now the final burn of the earthbound burn is now completed. It acquired the required velocity, and with that velocity it will simply go straight to the targeted point L1, but the L1 is also moving, Earth is also moving, Sun is also moving. So it's a combination of movements, and we hope that mathematically it matches exactly at L1, and this will continuously be monitored, because we call it orbit determination. So its path is continuously being measured using ground stations that we have. We have a deep space network, antennas are there. So it will measure the arc through which it moves, and we will make a prediction, mathematical prediction. It's actually moving precisely there. And it's moving such a far distance, 1.5 million kilometers. So a small error here can make a thousands of lakhs of kilometer error there.
Yeah.
So we need to very precisely identify. If there is an error, we better correct it at this moment. So we will decide on any corrections in 24 hours, 48 hours, etc. So as to make any final correction. And there are opportunities for correction between us.
Interesting. Tell me, where are all these things fabricated? I know your rockets are made in Thiruvananthapuram. These things, where are these fabricated?
It's fabricated at Bangalore at the UR Rao Satellite Center. Here itself, where we stand, this is a place where we build all the satellites. So most of the hardware from this came. Though the whole integration takes place here, but it has sources of these components come from various parts of the country in various ISRO centers. See, I can tell you, it has propulsion, for example, it has engines. You would like to go and see closer?
Sure, yeah.
You can see the engine there. See, this is the landing engine.
That's right.
There are 4 such engines, and there are control engines. These are fired to make it orientation change. So this engine plus its own feed system, the propellant tanks, it comes from LPSA Bangalore.
Okay.
And manufactured at Trivandrum, partly manufactured. The engines are manufactured at Trivandrum. Then tanks and propulsion elements are manufactured in Bangalore, and they come and assemble here. The cameras on this came from Space Application Center, Ahmedabad. So there are many cameras. There are cameras here. There are cameras in front. And when the rover came out, there are cameras which picked those images. There are cameras which will measure the speed, velocity, etc. So they are built at Space Application.
How many cameras are there on this?
In numbers, if you say it should be about
2, 3, 4.
There are cameras just for observation. There are cameras for measurement. For example, we have camera which measures the horizontal and vertical velocities of this movement. There are camera meant for looking at the hazard avoidance cameras are there, optical cameras.
Which you used.
Yes, for the last minute vertical landing. So it's about 8 cameras, I believe.
So where exactly you said then when these things are made here, and how many such payloads can you fabricate simultaneously at this place? Because your program is ongoing, all the
Here
time.
we have clean rooms and assembly facilities, we have test facilities. The total number of such assemblies possible is limited by the space and test facilities, checkout, etc. So I know that there is a record, even up to 10 such assemblies can be done at a given point in time here. So maybe at this time, if you go and visit some of our assembly labs, they will see skeletons of the satellites. Some of them reach little more mature level, some of them in finished conditions. Some of them are already ready and containerized. So I believe that almost 10 satellites can be built, and if they really stretch it more, I think it can be done more also. We have 2 campuses, one campus here, and there is yet another campus where another set of satellites are also
In Bangalore itself.
In Bangalore itself.
This kind of a payload, for example, Vikram lander, how much time does it take from start for it to be tested and saying now it's ready for launch?
See, if you start from the conceptual stage to realization, it's not a small short duration. It's a very long period of time. It could be as much as 6 to 7 years. But building instruments are the most complex part of it. And it goes through so many tests. And every test will make a change in the design. So we have concept of models. We will first make an engineering model, which is more resembling to the actual thing. Then that will go through testing, and that will reveal certain deficiencies. After engineering model is qualified, we make a proto generally. Then after proto it will subject to the flight-like environment of testing, then the flight model is prepared. This is a standard procedure. But if it's a proven satellite, for example, a communication satellites, we don't have to do engineering model, we don't have to do proto model, we make straight away the flight model. So the timeline could be reduced. But the most of the time taken is for procurement. Not really the assembly testing. Assembly testing typically 1 year.
1 year. So if you had to make a new communication satellite, in 1 year you can actually fabricate
Yes, if
it
all
from
items are ready with us, it's 1 year of assembly testing.
And how much of it is, when you talk about what percentage of the components are indigenous?
In spacecraft, if you look at spacecraft is more and more of electronics driven. It's not a mechanical or other systems. Other than high-end processors, chips, memories, and some specific radiation hardened devices, everything is Indian. But in terms of the money, if you look at those elements are very costly. If you look at the whole of this hardware, what you see outside is all Indian. But there are some still elements which is inside, which is the highly integrated circuits, memories, FPGAs, which you have no other options for, even detectors. We take years to get it. We have been progressively indigenizing them. So in terms of cost, I will say it is typically 40% to 50% of the actual expenditure of building it goes into those very small items.
That's right.
Okay.
Which you have to
Which you have to
source
buy.
from outside.
You have to buy. Whereas this number is almost 90% for indigenization content is almost 90% for rockets, whereas still it is 60% for satellites.
And you know, when you say that we very rapidly you have been moving toward indigenizing all your components, how does the quality compare with what you used to import?
So there is always a quality control processes. We have been indigenizing so many things in the past. For example, if you look at materials, most of the materials you use here are all Indian origin from Indian companies, and they are on par with the world. So we create a quality standards for them, which has to go through a certain amount of testing, validation, verification, etc. So they go through that. For example, I'll tell you, electrical cable which are used for wiring, they used to be imported. All spacecraft cables were used to. So today we don't import anything. It's actually made in India. 3 companies in India are making it, and we worked with them to convert those.
And these are these private sector
companies,
suppliers which you have.
Yes.
Other than cables and all, what are the other high-end stuff which private sector is contributing to your space program right now?
So many are there. For example, in terms of devices, packaged devices like gallium arsenide devices, memories, passive components, electronics, capacitors, resistors, PC cards.
They are being made.
They are all being made here. When you go in the higher end, then you will see sensors, optical sensors, all mirrors, all lenses, all optical assemblies are made here. All the materials that go into propulsion system are made here, including the high-end material which is made out of its columbium alloy, which is one of the highest sought after. It's a material made in India by Midhani, given to us. Then the solar cell, what you see here, the solar panel is indigenous, but the cell here is imported. Cell is still not made in India. You know, the commercial cells only are made in or photovoltaic power plants only, but the one which is used here, which is high efficient cell, still imported.
What kind of power does it generate with this solar panel once it gets the full sunlight?
See, here it depends on the orientation. It has 3 sides solar panels are there, but sunlight will fall only on this face in the nominal location. So it generates almost 1.4 kilowatt of power.
Which is good enough to take care of everything. And how much fuel do you still have remaining in your...
Our estimate is that after the landing process, hope process, etc., around 90 kilogram of fuel is left, which could be enough to do some more interesting maneuvers.
So those maneuvers are actually going to happen.
Let's hope. But there are many challenges, I must admit that. See, what happens is when the temperature goes below 180 degrees,
you don't know how the
liquids will not remain liquid, it will become solid. And every pipeline will become solidified. Every tank, every component.
You don't know what has happened.
And it has to melt back to the liquid. And knowing whether it is liquid still requires certain testing. And that we'll do. We'll try to understand whether it is still in the liquid stage. And with all our confidence, we will do something at that end of it, understanding.
You know, something different from this, you know, when you're looking at the countdown for a launch, you know, it says T minus whatever. Suddenly you get something and the computer says you have to stop. What is it that the computer is telling you that there is some error somewhere? What is it that is studying? The components, electronics in the system which says, okay, we have found something, it has to be set right. How does it happen?
See, in every launch, there are almost 2,000 measurements. 2,000 measurements, and it comes out of sensors, status monitoring, currents, voltages, pressures, strains, temperatures. So all this data comes in, and there are trends, and these trends can be understood by a doctor like you looking at your heartbeat. No, you go to ECG.
Yeah.
If I give you an ECG plot, can you find out anything wrong with my heart? You can't, because you are not trained to do that.
The system will.
But we people are trained to do that. So once you look at those curves or the graphs, you are able to understand what is a pattern, and if there is a kink in the pattern, if it's not moving in the right direction, there are expected bounds. So there are 2 ways of finding out. One is through the heuristic way of finding out. Through my expertise, I can find out. Second method is you can train a computer to do it. I will tell my data is going to be here, it will be within this bounds of this, and if it exceeds that bound, you give me an alert, and then I will look at it more deeply. When there are 2,000 data, human being cannot do it.
Correct.
So we train a computer algorithm, we call the automatic launch sequence, and that will check all the parameters. And when some parameters are out of bound, then it will immediately check some other thing to verify whether this out of bound is right or it's a fictitious, something can go wrong with the sensor. It's not a reality, it may be a false alarm. So to validate, there are other checks. So we call it triple modular redundancy. So if anything goes wrong, we check other 2 more things to validate whether the first error is the true error or not. So there are algorithms built around the whole of these measurements, which will decide whether something need to be stopped or not be stopped.
Interesting.
When some cases human being can decide to stop, many a times we can't. It has to be done by the computer only.
Okay. Now coming down to some of the projects which are being talked about a lot, Gaganyaan, for example. Where exactly are we in that race right now?
So Gaganyaan is a very complex project, though it's like launching something, but launching up there is very easy, but bringing back is very, very risky. And even for launching, we need to be very sure that nothing can go wrong because human beings are involved. We have given a very optimistic schedule when we started the Gaganyaan of doing it in 4 years of time. We faced many challenges. The challenges were in terms of the COVID that came in between. Almost 2 years of work suffered in industry, within us also. The procurement chain got affected, especially the high-end electronics.
It would still be affected.
It's still affected. So we are not getting the high-end electronics which are required for the human rated specification. They are still giving very long delayed schedules. So that's one domain. So we have to do many re-engineering, redesigns to overcome that challenges. But the biggest challenge to me is the safety of the crew.
Correct.
And see, look at the Chandrayaan project. Chandrayaan 2 landed in a problem. And to make Chandrayaan 3 took 4 years. Suppose you look at Gaganyaan, if it happens, the first mission ends up with some problem, recovery will be very difficult. It could be 5 years, it could be 10 years. So I talked to my
human beings involved. No?
Yeah, so I talked to my teammates and also talked to government also as well, and mentioned to them saying that it is very risky to go a fast track approach in this. It has to be a very cautious approach with the full confidence on the very first mission. So we thought that we should add additional tests, additional validations, additional measures to ensure the first time when we do it should be right. So this
you can't go wrong.
Of course, in no mission we can go wrong. We are answerable for it. But the most important part is that ask a question to ourselves: have you done what is necessary for this to go? And in that question led us to adding more tests and more validations, etc.
Yeah, it takes
so we
time
reframed the whole project. Of course, it is of course discussed with the government. It is also going to be discussed with the Space Commission and many other fora. And we would like to set the clock slow for it.
But some idea about?
Yeah, what we are trying to do is there are many tests, hundreds of tests happening now. And we would like to make sure that in the next 1 year, most of those tests do happen. And manned mission, of course, the final manned mission cannot happen before 2025. This is what we have identified. And that is based on all success criteria, that we go through all the tests.
Yeah, all the procurements and whatever is required.
Everything happens very well. And the biggest test which is going to happen, the crew abort test, is going to happen next month.
You say 26th?
Yes, 26th of
October.
Yeah.
Okay. All the best for that.
Thank you.
Okay. So, we have always used the phrase rocket science. For the first time, we are getting used to or understanding what it exactly means. So, I want to understand some more about rocket science. This is the model of Chandrayaan 3. Why is it that we took 40 plus days to get there, whereas the Russians, even though it was a failed mission, made it there in just about 5 days?
No, it has to do with quite a lot with the rocket which they used. The rocket we used is the LVM-3 rocket, which has a capability of 4 tons to GTO. And the corresponding payload capability for putting the satellite in an orbit, which will directly take it to moon, needs little more power. Typically, if it was around 6 tons to GTO, possibly we could have done that. But we are at a lower threshold of it. The Soyuz rocket, which took the Luna 25, had that type of capability, because their upper stage is very powerful upper stage, which actually did the final boosting to put it in the translunar tract right away. So they could travel in 5 days of time. So when the rocket is not powerful, what you have to do is you have to make the satellite more powerful. It should have a propulsion which should be able to do that translunar injection. But that also cannot be done in one go. So that's why we have to do a maneuver which is moving around the Earth in multiple passes and do the energy addition or the velocity addition at the most efficient manner. So, and that also cannot be done in a long duration firing. So, you know that every movement around the Earth is in an elliptical orbit. When it is closest to Earth, we call it perigee. the closest point, apogee is the farthest point. In the perigee is the highest velocity zone, and if you can impart the energy to it at the closest point instantaneously, that is the most efficient, but we cannot do that. We have to do it over a period of time, that we will end up with some losses called arc losses. So, we minimize that and do every orbit a little bit of addition. So, ultimately what happens is the propellant that you are consuming to do the energy increase is minimized, and this is done in a manner which is optimum from various considerations. One is fuel minimum, we have the visibility from ground stations, etc., and also the overall mission plan. So, it is done in multiple phases to raise the orbit, so that the last orbit firing will raise it to such a level that the final orbit will encircle the moon. So, that is how it took more time around Earth. Then second is around moon also we took more time to first inject into a highly elliptical orbit, a big orbit, progressively reduce it, same technique we used so as to minimize the fuel. So, that is why the Chandrayaan 3 craft has two parts. One is the propulsion module, which you can see here. From this point to this point is a hardware just to take the lander to moon. The purpose of the whole of this is almost 2000 kilogram of propellant. With its solar panel for power, control, everything is just to take this craft up to the moon. As if this was part of the rocket, then you will say the rocket has done the job, but for that it requires much more energy, because we are going to do with a stage which is much more heavier. Correct. So, not an efficient method. Typically satellite engines are more efficient, and once the rocket part goes away, the mass comes down, so you can make it do more efficiently. So, this is a new way of doing it, and we had done right from the Chandrayaan 1 time onwards. We did it for Chandrayaan 2, we did it for Mangalyaan, and we did it for Chandrayaan 3 as well. So, it is a approach which gives you very fuel efficient capability, but we do not have to make a new rocket for it. No?
Correct. So, what happens to this after it then disintegrates?
It does not disintegrate, it actually goes to an orbit of 100 by 100 kilometer around moon. It is still there, it is working, but we made this time that this is not a functional element today, because its job was only to take the lander up to the moon orbit. Correct. And then afterwards it has no function. But we have one payload on it which is called shape payload today, which is going to do an observation of Earth. So, that is continuously doing measurements.
And what kind of measurements does it do from there?
It is actually looking at Earth in a spectral nature of the Earth is measured, and it is trying to find out the similarity between Earth and a future exosolar planet, that is a planet which around any other star, not moon, sun, if you ever discover. If you are able to get the spectral characteristic of the emissions coming from that object and the emission coming from Earth, if you can find certain comparison, you can say the life controlling emissions, which is of various nature, now presence of water, presence of oxygen, presence of bio systems, etc. So, if you can characterize the Earth in a spectral manner, then you can characterize that object's emissions through the atmosphere of that also in that similar manner. So, it says that by this comparison you can say this planet is habitable or not habitable. Simply an interesting experiment.
That brings me to this, about how we are studying what is there. Anything which Pragyan or Vikram have sent so far about the moon surface which we have not disclosed to the world as yet?
Yeah, there are interesting things. For example, the moon's topography, the surface characteristics. We did two important measurements, which the initial findings. I am not telling the detailed scientific outcome. There is a payload called Chaste, which we pierced a probe into it, which is a composite material. Inside there are heaters, which apply some heat temperature and measure the temperatures. The temperature should measure certain distribution and also measure the thermal characteristic of that material, and also look at how the surface is like a very thick, very good insulator. So, we found that even though the upper surface is room temperature, little higher temperature, within 10 centimeter down the temperature has gone so much less. So, that means the heat transfer into it is through very, very less. This is a new finding. Similarly, the rover, when it actually moved on the surface, the wheel, and also the landing process, we were expecting a lot of dust, dust to lift off, because the engine is giving jet at a super hypersonic velocity. The whole dust should stir out and then cover the whole thing. Nothing was seen of that type. We found a very mild dust coming out, not huge dust, but that was surprising. But then after landing and the rover came out, we couldn't find much of the dust formation on the track or And finally, what we found is the surface is not very dusty. It's actually chunks of the soil is coming out. When the wheel moves, wheel has certain impressions. The impression is actually taking out the soil in form of blocks, bricks like. That means there is something sticking together. It's not very, very dusty or powdery, which is a very important finding. Why it is it's not so in that zone? Because whatever data that we have collected from various other sources for people who have already gone to moon, collected the samples, especially in the equatorial region, we are speaking about dust as a major issue.
Correct.
And we didn't find it to be a major issue in this zone. So definitely it's an interesting finding, and it needs further investigation. What makes it to be like that, and what are the materials that make it to be like this? It's definitely not water, of course.
Sure.
Okay.
We are in the assembly, integration and testing clean room facility 2. Tell us, what exactly do we see here?
See, that's a satellite which we have just now completed the integration, testing and ready for launch. It's called XPOSat, X-ray polarimetric satellite. This is going to be launched using a PSLV soon. It's one of the scientific mission that we wanted to study basically black holes.
Okay.
And basically what happens is when black holes eat into other objects like the stars, suppose another star comes closer to black hole, there will be a material attrition which will be drawn because of the huge gravity in the black hole. The material will start flowing like a tunnel into it. It will generate so much of radiation in the X-ray domain. And this radiation, if you are able to do the polarimetric measurement of it, you will be able to get an idea about the type of the pairs which are actually existing.
This is the actual payload being...
So what you can see on top, it's basically, that is a payload. It's an instrument which actually measures X-ray straight from there. It measures in the polarimetry of the X-ray will be done. And that is the only instrument basically this is doing it.
And when is this scheduled for launch?
Actually, we have not scheduled the launch yet. We wanted to complete this current launches of Chandrayaan, Aditya L1. We kept it in the cold storage for some time.
Okay. And how much does this weigh, this whole payload?
This weighs 450 kilogram.
Okay.
Yeah.
Okay. And what are all these things here which we can see right now?
Each of this is a station where one satellite can be assembled.
Okay.
So this is a test fixture which you can move in different directions, tilt it up, orient it. When you want to assemble, it's a station where, like automobile assembly station, you will see.
Correct.
It's similar to that. Then it can move on its wheel to the test assembly or checkout or clean room or wherever they want to go. So so you can see one of the structures there. This is, I believe it is called IDRSS. IDRSS is an Indian data relay station, a satellite, which is supposed to be built under part of the Gaganyaan program.
I see.
When the crew module is in orbit, they have to maintain communication between Earth and crew continuously. But we don't have ground stations all across the world. So what we do is the crew will communicate to this satellite will communicate back to us. So this will remain in geostationary orbit. So we have to build 2 such satellites and launch prior to the Gaganyaan program. So
that, when you talk about satellites and communication, there's a lot of talk about NAVIC.
Yes.
When do you see its usage as much as you see of GPS and GLONASS?
See, first of all, you have to understand the NAVIC is created for a different purpose. It was created for a strategic purpose.
Correct.
And it was created when there was a denial of GPS to us.
I remember, yeah.
So then the primary objective is to provide services to the strategic forces, for them to do position timing and navigation services for their fleets, for their equipments, for their weapons, naturally. And it has to be much more accurate than GPS. So typical GPS gives you an accuracy about 20 meters. Could be better also. But we have designed NAVIC for an accuracy of all 3 meters, because it is based on the stationary set of satellites, not a moving set of satellites. And it is actually demonstrated. But unfortunately what happened is, after our launching, the penetration of that into our defense forces has not been very strong. Also, it didn't happen due to whatever may be the reason. So I have taken it up much more seriously, and the present CDS also is very keen to make sure that it actually happens. We had a series of meetings to make sure that it gets into the Army, the Navy, the Air Force and all their equipments. The equipments which are inside are mostly GPS based equipments, and to convert from GPS to NAVIC requires a lot of work in terms of hardware development, change over a period of time. But they are on the job. I believe in another few years that transition from GPS to NAVIC will happen.
I see.
Second point is that, of course, when you have a capability, it has also a civilian signal. Now, the civilian signal should be used by civilian people, and we have given a lot of thrust to that in the last past. But the civilian utility was affected because of various important reasons called the frequencies. So, you know, GPS is operating in a band called L1 band and L2 band, whereas we were denied those bands by GPS long back. So, we built the Navic around two other bands called S band and L5 band. So, these two bands are not there in your mobile chips or chipsets.
Happening now though.
So, we said that for anybody to use this in mobiles, they need to have an additional chipset in L5 and S band, which is creating problem for them to additional cost, additional infrastructure, etc. is required, antenna required. So, we decided that we have to add L1 band and L2 band into Navic. So, we built it and launched satellites in L1 and L2 band now, and also we launched a highly encrypted strategic signal also. So, last Navic launch onwards, this series has now started. Now, recently you heard that Apple has announced their L1 band based Navic. Now, I believe it will become popular in civilian sector like vehicle fleet tracking, railway tracking. It's already implemented using L5 and S band, but with L1 band, it will become more popular.
Interesting. Okay. So now, and what is this structure here? It looks like
these are all places for putting their checkout. I think right now they are using it as a store.
Okay. And this is where you said
this is where they had that crew module assembly. That's just happened. It has left.
Now it has moved to.
Yeah.
Okay.
It has moved to Sriharikota. The back side is the checkout place. I think they have all moved.
How do you transport things from here to Sriharikota?
We have containers, huge containers, which will be kept air conditioned, temperature controlled, purged typically by nitrogen gas, and move on the road.
And tell me, do you get any special green what do you call passage or something, so that you don't get obstructed anywhere?
We have pilots and warning. We inform all the civilian authorities about our travel. Sometimes the power cable shifting has to be done, but generally our track is all surveyed now. So generally hardwares are able to move
with the normal traffic.
Traffic it can go. Yeah, but we try to move it in night time or daytime where the traffic is very small. Otherwise, we park somewhere identified locations.
And there is security around.
Security, with all security it moves.
Yeah, because these are strategic.
Yeah, the cost of this will be in hundreds of crores.
Absolutely.
When it moves really.
Absolutely.
Yeah.
So, how many clean room facilities are there altogether?
Here we have two major clean rooms. Then we have clean rooms, two clean rooms in another campus.
Okay. Coming to when you're talking about how long a satellite or a payload takes to assemble and then get ready. Now that you have proven yourself to be very successful with not just everything actually to do with space, from the launch to releasing satellites to landing and everything. How does that? What impact will it happen to your effort to commercialize our space program, so that you earn like every other nation does?
See, space has a commercial activity which is more into the downstream. The launching of a satellite, like with a rocket and launching and make it commercially successful, is difficult. I think there are not many people who are actually doing launching as a business. It started with Arianespace in Europe, but it's also heavily subsidized. I think you must realize that it's Europe's own launcher capability subsidized heavily by the nations, but they do also the commercial service, and they have never been profitable. And they are now almost Ariane 5 is closed, Ariane 6 and Vega are coming up, again hoping to become a commercially successful entity, which is very difficult. Now, the other activity which happened in US, the Titan, the Delta, they are never successful in terms of commercial ventures. They were mostly dependent on government launches and strategic launches. Then came the SpaceX. Now recently, because of the reusability, they are reasonably successful in commercial domain, but still I understand they are not fully breaking even with this many hundreds of launches taking place. Becoming a very profitable in rocket business is very difficult. So essentially what happens is launching continues to remain as a national strength, and it is supported by governments to remain like that so as to protect their national interest. Okay, so this is the geopolitical meaning of rockets. It's very, very critical. But building satellites have become already commercial. It is happening in the private ecosystem. Even in India, we have started companies building satellites on their own. Even clean rooms of this class are come up in private now.
This is class what, clean room?
This is 1 lakh class.
Okay.
This is 10,000? portion is okay. Generally, you can say it is 1 lakh class.
And do you have what kind of a thing? Do you also have laminar flow technology at some places where only
That
the
will
hand
be
goes
very,
in and
you
does
can,
things?
you have 10,000 class area, you can have even 100 class in small areas in laminar flow tables where you can do some assemblies, where device assemblies are taking place.
Is it happening here
10
somewhere?
There are so many labs here.
Okay.
Some-
Is it possible to take a look at them
you
from
can,
outside?
you can go, you have to go to the other campus.
That's fine. Okay.
Yeah.
Okay. Tell me, how do you manage to keep your costs so low?
The principle of keeping cost low is coming out of the approaches that we are taking. See, first thing is that models, for example, if you get into design of a model, you have to invest in prototyping. Then prototyping is actually in multiple levels of prototyping are minimized. You go for a very minimal prototyping. Then most of the designs are not outsourced. It's actually done inside. So right from the conceptual design, the PC card layout, the component soldering, making, the proto engineering, the softwares, the test equipments, all done by our own people. In fact, we created a method by which no design is outsourced. Not even the ground system design is outsourced. You look at this fixture. Even this fixture I could have purchased from somewhere, but this design, drawing, everything is done in-house and manufactured. So it looks so simple, but when we recently sent one to US, I'll tell you one interesting story. We wanted to assemble one satellite called NISR, NASA ISRO Synthetic Aperture Radar. When this payload structure was sent to NASA, they so much liked it. They said, you retain it here, don't take it away. We want to have one like that.
Really?
Yeah. They never thought that such a beautiful assembly fixture could be made for. See,
And this is all in-house designed
in-house
and
designed
developed.
and manufactured by local industries here in and around Bangalore and other places.
What is this made of?
It is a steel structure, but it is motor driven. So you can rotate this with its actuation. The whole thing can rotate like this. It can be indexed at different orientations.
It can be taken up and down.
Yeah,
You can
up and
see
down.
that, huh?
Yeah, it can go up and down. It can also rotate.
Yeah.
This also can rotate, right? Yeah. So it helps you to do testing. For example, antenna want to test a feed test, you can move it. Illumination test, you can do testing. So even such small thing, it's also done here. And you can see in that room there will be hundreds of test equipments, and every test equipment, ground system, its software, communication equipments are all designed by our own people.
So
And
that is
see, suppose you work with contractors. The approach for contractors, it actually doubles up your cost.
correct.
So one is do it as much as you can in-house. And the same technique is being followed by SpaceX, that they put everything under one umbrella and try to do it by their own people. They bring down the cost drastically. So this is one approach. Second is minimize models. Then go to straight away to the flight options as much as possible. Then of course cost comes down account of the manpower cost being lower here. It's naturally lower. And we have seen that in high-end manufacturing, US also finding it extremely difficult. We
Correct.
talk to in American companies, their cost of production of any unit is much higher there. If you do the same work here, even then it is coming out to be much more cheaper.
You talked about manpower very interestingly, Stuart. What is your feeling about, are you able to attract the best talent available in the country?
It's a very big question. If you say, are you getting the best talent? The answer is no. See, for example, our best talents are supposed to be in engineers, they are supposed to be in IITs. No? That's what we believe. No?
Correct.
But they are not joining ISRO. If I go and try to recruit anybody from IIT, none join.
No one.
No one
Do you
joins.
have anyone from IIT in
There are
ISRO?
a few people who think that passionately space is important, so such people join. But not many. The percentage is hardly less than 1% or even lower. In fact, I'll tell you one example of such a recruitment. We recently, one of our team for in situ recruitment went to one of the IIT. I won't name that IIT. And they were presenting to them the career opportunities in IIT, the pre-recruitment presentation. And after that career type of work, etc., they presented the salary structure, pay structure of the ISRO system. And students who are sitting there, they saw the last pay of the highest pay that you can ever get in ISRO. When they saw that, that's it. And just after the presentation, 60% of the people sitting in the hall just walked out.
Can you imagine? Yeah.
Okay, so you can imagine, because the career ambitions of the people who are joining IITs are
They
different.
probably they start with whatever
Start with
the
that
last
salary,
is.
yeah. So money cannot attract people here. Then the next question is, are we having adequate talent to do the work that we are doing? The answer is yes.
Yes,
Yeah.
that's
So
very
the question is,
heartening,
are you getting the best talent versus the adequate talent? See, if you look at our Indian system, the talents are spread out over a very wide spectrum of social strata. It could be in IITs who get an opportunity to write an IIT examination, go there. But many thousands of lakhs of such people who have competency of that nature are not ever getting opportunity. I am one of them. When I was a student, I never had opportunity to write an IIT entrance to go to IIT. But it doesn't mean that I was a naive or not knowing person. So lakhs of such people are not writing that exam at all.
Tell me, after the successes, repeated successes that we have seen, have people from outside written to you, we want to get involved now, Indians?
Yes, yes, so many of them
Who are very successful outside.
Very successful people, senior people are writing to us that we want to contribute to space in some way or the other.
In India?
Yeah, they are always telling. But the opportunity for such engagements are not like the US or Europe, no? Here we have to be an employer. Our terms of contracts are governmental rules, no? I cannot hire a person from a private industry, engage here for a work. Those limitations are to be overcome.
I'm just thinking aloud.
Yeah.
Do you have an experience center kind of a thing here where school students, and others can just come and experience how it is done? Just makes them excited about the whole
We
thing.
are doing it continuously. We bring a lot of students here in this laboratory. We arrange programs at various occasions. We have in space weeks where thousands of students visit us. We also go to schools. We do presentations to them. Typically in a year, almost a few lakhs of students are connected by ISRO. Various ISRO centers. Yeah.
What about if people want to buy models and badges?
What we have done is we have created a merchandise contract. We signed contract with almost 25 different agencies, and they have been licensed to produce, manufacture ISRO merchandise, and they sell it across the country.
But why is it not publicized a lot?
It is publicized in our website. You can see that the list of merchandise available: T-shirts, logos, badges, models, satellites. It's all available now in the public domain.
So, after the great success of Chandrayaan 3 and Aditya, which is still ongoing, what are the next things that one must expect from ISRO as far as space program and other things are concerned?
See, if you really look at the activities of ISRO, we have been all the more focusing on operational systems like launching communication satellites, remote sensing satellite, meet the national demands, then do some science missions as an off-take of all of this. No, they were occurring very short period, very long periodicity. Typically 2 years, 3 years, we had one mission like Chandrayaan 3. But this has given us a great confidence. No, we must continue to do the exploration, scientific missions in much more frequent manner, and also set higher goals. No, not just go to moon and do some landing, but set higher goals. Then the question is, what are those higher goals? The question is that we have one track called Chandrayaan track. No, we have done Chandrayaan 1, Chandrayaan 2, Chandrayaan 3. We also did Mangalyaan 1. We did. We also did Astrosat. We are going to do Exposat. There is yet another track which is called Human Spaceflight track, where we are going to send human beings to space. We also looking at the reusability, etc. So, can we fuse all of these ideas into one unique idea in which humans will one day go to moon and land? Why not India think about it? How do we really put a space station in orbit tomorrow? Why can't you do docking on a space and then imagine little more stronger ideas in space than what we are telling, do small things. So we are enthused by the success to imagine even those type of things, and with the capability that we have today and the type of capability that we are likely to develop in the next few years from now, we are envisioning that we should be sending a space station soon to orbit, which is just not for show. It's actually for a scientific objective. We realize that going to space station, doing robotic activity is so crucial for industries. It is to make new materials, it is to do medical synthesis, maybe organ printing in 3D, or continuous R&D on human habitation there, etc. Gaganyaan is anyway going to happen, but beyond Gaganyaan what? Whether it will be sustained, continued as a continuous human spaceflight program, this question we are asking, and how to sustain and why to sustain, this answer should come. And if you have to merge this Chandrayaan program to Gaganyaan program and convert it into a human space flight to moon and land, maybe in the Amrit Kal 2047, then it is a great thing.
Correct.
So we thought that why don't we work on it? So it requires a continued exploration of moon and generate more and more indigenous capability to go to moon and come back. So the HOPE experiment which we did recently is a precursor to that thought process. After landing softly, if you are able to take off and come back to Earth, So I am asking this question to our own team. Why don't you do that? Why don't you come back to Earth? So we are working on how to do it in very short time. How to bring some samples from moon to Earth and then do scientific studies. Scale it up to a level that we can actually send a robot to moon, do some exploration, bring back more scientific outcome. Maybe a few years from now, an Indian will definitely land on the moon. There is no doubt about it.
On an Indian satellite, launch vehicle.
On an Indian launch vehicle, of course. We are not going to take launch vehicles somewhere else.
No, when I say, not as a partner with somebody else.
Partnership is always important because even for this Chandrayaan 3, we had partnerships of various kinds. Partnership will happen, but the primary design, primary execution will be by India, no doubt about it.
Okay. And anything else with these kind of materials which are being developed, which are the smart material being developed, which the world is talking about simply because of how you achieved it at such low rates again? I'm keep coming back to that question.
Yeah, we have been all the time concentrating on doing it within India. I must tell you. For example, the materials which we are using for our rockets and satellites are reasonably high percentage indigenous. Most of the metals are made in India. Metal means alloys of very high class. But the production is still not, in private sector, is still not very up to the mark where it is profitable. For example, aluminium, we still have to import. Though it is abundant in India, but high quality aluminium is still not made in India. It is possible with some investment. We also know that composite is very critical. We are very poor in terms of its high grade composite manufacturing. The low grades are still manufactured in India. Same is the case with electronics. We are manufacturing low grade electronics components here, but the top notch electronics is still not manufactured in India. I think we have to focus on all this. I believe that if you have to really become a world leader, these three areas are so critical. Very high end materials, very high end composites, very high end electronics. We must focus on it. And this is the only way to generate a clear revolution in this domain.
Correct. So it's been an absolute pleasure to be shown around this place and understanding what rocket science exactly means. Thank you so much for giving us the time. It has been an absolute pleasure to have you take us around. Thank you so much.
Thank you.